Here we go. The problem one, this is about a rocket. This is sort of a typical thing you might have to do on the project using your spreadsheet. So all these numbers you're going to be collecting or figuring out using some kind of means. Some things like the density of the air, I'll provide that. But these other ones you're gonna figure out from slow motion video and other means. But this describes really the way your rocket starts out and the air around it. And then we're going to use a spreadsheet to find all this stuff. So I'm just going to start populating the spreadsheet. And maybe I should split my screen to do this. All right, so let me zoom out over here a little bit and zoom out over here. Hopefully you can still see that. I'm going to leave G as it is. It says the initial velocity of this rocket is 56 meters per second, so I'm going to put in 56. And upward just means positive. The mass of the rocket is 0.182. And this is after all the water is gone. So it would have been heavier than that during the acceleration period. The air density is 1.27. So I'm just putting this in these yellow cells over on the side. Make sure that you don't put any units in there because it won't know what to do if you put units in. Like if I put in kilograms, everything turns into weird numbers down here. Cross-sectional area, we're just leaving that 0.01. That was the default when you made your spreadsheet. Drag coefficient, this is a better rocket, 0.25. It's got a lower drag coefficient. Time increments, let's leave those the same. The rocket is going to be at a height of 2.4 meters, not 3.4. So this rocket squirts the water out and then it pushes its air out and then it's done with thrust and its height is 2.4 meters. Its velocity is this and it's moving through air with that density with this drag coefficient. So I think we've got everything we really need here. Oh, the time, 0.055. So initial time, I'm going to change this to 0.055. So that's the time at which this is going to start, and this starts right after thrust ends, and thrust ends there. So find the total time aloft. Time aloft is right here. So that's 8.065, 0.065 seconds. Maximum height is right there, 78 point, I'm just going to call it 78.9. Meters. Meters. Oh, goodness. I'm going to have to do some sketching here for this next part. And I'm opening up my whiteboard. That'll take just a second. But while that opens up, I could be talking about the answers. So for the moment just before the rocket lands, I need to sketch the rocket and show all the forces on it and the net force, et cetera, et cetera. So let me get to here, do a new whiteboard. Bear with me. I don't know why they put dots. Who would want dots? So this is the rocket coming down. I'm going to make a really nice rocket there. And here's the ground. So when it's coming to the ground, it's moving downward. So drag is pushing it up. And its weight is pulling it down. And those are the only two forces. Those two forces together are going to add up to the net force. All right, got my drawing ready to go. Let me go back to these two things. So I need to show the rocket. I've already done that. All the individual forces, I've labeled them, but I haven't calculated what they are. And then the net force and some more stuff. So to find the individual forces, I'm going to make this a little bit bigger. And so there's drag. These are all the drag forces, and this is weight. Those are the only two forces. But this is at the beginning. What I need to do is find the end. And to find the end, I'm going to look at Y position. So if you look in column G right here, let me zoom in. Column G here. These numbers are getting bigger. So I keep going, it's getting higher and higher and higher. zoom out a little bit. And when I get to 78.8, you should see it go down. So this is about as high as it gets. These numbers over here, these are how I'm figuring out this time. So this little statement, if B357, if y velocity is less than a certain amount, then I know I'm at the top. That's one way to do it. Anyway, I'm going to keep going. I need to get to the crash down, so I'm going to go fast. I'm going to grab the slider over here until y position is 0, or almost. There. So here the y position is 1.38, here it's 0.22, here it's negative. So right here, this is what I want. I want row 809. So at that moment, the weight is 1.7836 downward, and the weight never changes. The drag is 1.33. So let me put that into my answers. 1.78 and 1.33. Oh, no, I need to put it on my drawing. .78 newtons, 1.33 newtons. So I could find net force by subtracting this minus this, 1.33 minus 1.78. But I've also got that in the spreadsheet. Might as well take advantage of the spreadsheet. The net force is negative 0.45. So that's because that's what the spreadsheet is doing. It's subtracting those. So the net force is, I'm going to call it 0.45, and I'll just use a down arrow. So the net force is down. Let me get rid of that stuff. And since I know the mass, I could use net force equals ma to find the acceleration. So here's the net force, and the mass was, what was that mass? It was 0.182. Mass equals 0.182 kilograms. So I could use those two and I could find A. Plug that into here. Or it's already done on the spreadsheet. So the y acceleration, there is no x acceleration. We're just working in the y dimension. It's negative 2.47. So again, erase all this stuff. Acceleration, oh, one more thing to erase. Get out of there. Is 2.47 downward? Let me check. Did I do that right? Yeah. All right. So I've got taken care of the individual forces, the net force, the acceleration, the velocity. I need the velocity. So y velocity, lost track of my rows again. It's row 809. The velocity is negative 28.9. I'm just going to round that to negative 29. And I think I'm done. So I've got the y velocity, the acceleration, the net force, and the individual forces acting on it. So that's done. Now I'm supposed to do the same thing again, except just after thrust ends. Before I do that, before I go on to this part, I want to show you something. So the y velocity right now, 28.9. The terminal velocity calculated up at the top is 33.5. So this wasn't able to fall far enough to reach its terminal velocity. If I keep going down to 1,000 rows, our calculations still don't go long enough. So it would need, this is after it was flying for almost 10 seconds and it's fallen into a hole about 60 meters below the ground. It's still not to terminal velocity. And you creep up on terminal velocity. The closer you get it, the slower you approach it. Now I need to change some things. So we need to focus on a time of 0.055 seconds, which is very easy. That's the very first time. So now we can just look at row 9, to get all the information for this drawing. So I'm going to make a new drawing and make an even better rocket this time. Let me give it another fin. So as this rocket's going up, there's still weight on it. And, oh, what am I doing there? There's nothing pushing it up. There's no thrust, but there is drag. Which would you guess is stronger at this point? So the weight shouldn't be any different. The weight's still going to be 1.78 because the weight is dependent on mass and gravity, and neither of those is any different in this picture and this picture. They're both after the water's all gone, so that's the dry weight. Now the drag in the very beginning is going to be big because it's going super fast. So the Y drag is negative 4.97 newtons. That's over a pound of force acting on this rocket. And it's creating a net force that's really strong, so we're going to have a big negative acceleration. Okay, I'm going to do that. Maybe I can see both things at a time. So the drag force, I'm going to make this arrow bigger because it's a stronger force than that, is 4.98 newtons. The net force, if I add these two together, they're both negative, they're both downward. I'm just going to write it as a positive and show that it's down. The net force is 6.76 newtons downward. The acceleration, I can just copy this. I could calculate it with the net force and the mass of the rocket, but you can see it's right here. Negative 37.2 meters. I'm just rounding, meters per second squared. So it's slowing down really fast. It's going very fast, and it's slowing down fast compared to how quickly this one is accelerating. How fast it's speeding up as it's falling, that's much smaller. This is a much bigger acceleration. Both of the accelerations are downward, so to be consistent, I really shouldn't put that negative in there. Let me just do a downward arrow. And sorry about my alarm. Let's see what else I'm supposed to do. So I've got all the individual forces. I have the net force. Oh, I need to find the velocity. The velocity is just the starting velocity, 56. I don't know if I wrote the velocity on the other one. Velocity, let me write it up here. Velocity equals 56 meters per second. Did I write it on this one? Yeah, velocity is negative 29. Okay, so that takes care of the ones about the rocket. Now number 2, this is about a wiffle ball and a baseball and somebody throwing them straight up. I'll do the wiffle ball first. So we're supposed to find the cross-sectional area for each projectile. How high are they going to go? How long are they going to stay aloft? And then it's going to have a comparison, which is kind of annoying now that I think of it. First, let me do baseball, and I'll find the cross-sectional area. The diameter of the baseball is 7.4 centimeters. So I'm going to off over here. I'll just use this to calculate. So what I want to do, I guess, first, let me just write 7.4. And I'm not labeling. I'm going to convert this to meters. Equals this. There are 100 centimeters in a meter, so that divided by 100 gives me the number of meters. But that's the diameter. The radius, which is what I want, is the diameter divided by 2. So I'm just going to write base ball radius. You don't need to do this. This is ball diameter in centimeters. This is ball diameter in meters. And this is the ball radius in meters. So I can use this, in meters. I can use this again when I do the wiffle ball. So cross-sectional area. In meters squared is going to be equals pi. This is how you do pi. You could do 3.1415, whatever. But if you just do that, pi, open and close your parentheses, that's going to give me exactly pi, or at least pretty close to it, times this radius squared. So there. So I need to put that in for the cross-sectional area. I can do it like this, equals that. It's very, let me fix that. So it's very small, 0.004, 4 thousandths of a square meter. The air density, I'm leaving at 1.27. The mass of the baseball, I think I said it was 0.145. I should check that in just a second. I think these things are being thrown up at a velocity of 30 miles per hour. So I'll check in just a second. But if it's 30, it's 30 divided by 2.24. That gives me meters per second. And again, why is it changing the formatting? So 13.4 meters per second. Drag coefficient, it says is 0.5 for these. So let me go back and confirm that my numbers are right. So the baseball is 7.4 centimeters and 145 grams, which is 0.145 kilograms. Drag coefficient's right. The one thing I haven't, okay, I guess I have done everything. 30 miles per hour. Make that bold for you. Right, cross-sectional area for the baseball, it's 0.004. And for the wiffle ball, it's 7 centimeters. So put in 7. 0.0038. Doesn't matter if you're really super precise, I guess, in your answers. I always put an H in a wiffle ball. It doesn't have an H. And the baseball was 0.0043008. Maybe I will be precise here. 0.003848. How high will each of them go? So what I've got in here right now is, I need to undo that. So I have the right cross-sectional area. This is the baseball. The baseball goes maximum height of 10.9 meters, which is, if I do that divided by 0.305, that's 35 feet. Doesn't seem very high. Can check that in a little while. So baseball, 10.9 meters. And how long does it stay aloft? Let me shrink that down so I can see both of these at once. Baseball stays aloft for 2.875 seconds. Oh, crud. So there are a few funny things going on here. I should have set this up for